Hi everyone, this presentation is intended to give you a little bit of help when it comes to your revision for your S2 end of year assessment. Throughout the year we've been really happy with how you've engaged in all the practical tasks and the work throughout the year, so it'd be great if you could demonstrate that in your final assessment. We don't want you to do all that work all year and then not prove how well you've done in the end. So work your way through this presentation. This is not all you should be doing, but it should just be a little bit of a guide, a wee bit of a refresher of the things that we've done throughout the year. Okay, so your first step should be having a look at Schoology. You can see we have folders for every one of the units that we've gone through, and then when you open up those folders you can see all the individual files that you should be working your way through. Now again, this is just to recap the things that you've done. None of this should be new to you, and so it's just about consolidating your learning. Use these resources in order to make up your own notes, which are going to help you when it comes to the test. Now, because this year the end of year assessment is going to be an online quiz, it's going to be very similar to the homeworks that you have carried out throughout the year. So one of the most valuable pieces of the revision that you can do is to go back to all the homework TMAs and reattempt them. By practicing this, the knowledge will become second nature to you, and I think that you'll find the quiz questions that we have in the final assessment will be a lot easier if you carry out this process. Now, we started off with vector graphics, and one of the things that you should probably be thinking about are the tools that we use within that package. So make sure you can go through these and describe and name these different tools. You probably saw this in class at the time, but as you scroll through these, which property has changed? Is it fill colour? Is it stroke colour? Is it stroke thickness, shape, size and position? So I'm just going to go through these just now, and you can pause, you can take a few seconds to remind yourselves which one of these properties has changed in each of the images. So we talked about the different properties that we can have, such as line thickness, but what about the different operations that we can have? If we started off with this man facing this way, think about how he would look if he was flipped, if he was rotated. This is obviously if he was scaled down, he'd be slightly smaller, but all the proportions are exactly the same. Skew is one operation that people always forget or find it difficult to describe, but basically it's like pulling one of the corners away from the rest in order to kind of scale it. You can see in this example what effect it has had on the original image. Then we moved on to the bitmap unit, and again it's useful to be able to look at the toolbar and name and describe all of the tools that we used in Fireworks. Again, it's a good idea to pause this part of the video in order to have a good look at all of the different icons in order to make sure you can do that. Again, I would advise you to make up flashcards perhaps for this part in order to be able to revise this properly. This image should just remind you of how bitmap graphics are actually saved. When it comes to vector graphics, remember it's the properties of each shape which are saved. When it comes to bitmap, as you can see in this image, if we were to go from this part and increase the size or zoom in, we can see every individual pixel which has made up this image. Now this is the fundamental part of bitmap graphics. It is a map of bits, okay, and we'll get to that, but for now we can say it's a map of pixels which make up this image and every bitmap image. If we were to look at how a computer would see an image, it wouldn't actually see it as the one on the left hand side, okay, as pixels. It would actually see it as binary numbers. Now we should know that binary numbers are made up of ones and zeros, and if it was a black and white image, every one of the pixels, as you can see on the top line, would become a 1, and for the computer, whenever there was a black pixel, that would be represented as a 0. But what happens when we don't have black and white and we want to represent millions of colours? Well, in the black and white example, we used 1 bit for every pixel colour. If we want to use more colours, then we need to use more bits per pixel. You can see in here, every one of the pixels uses 2 bits in order to save it. That means that we can have 4 different colours: 0, 0, 0, 1, 1, 0, and 1, 1. That means that this colour might be white, this colour might be red, this colour might be yellow, and this colour might be black. This diagram shows that the more bits we use, the more colours we can have. By using 4 bits, it allows us to have 16 different combinations, all the way from 0 to 15. Okay, and that allows us to have a lot more colours. The first example that we saw only used 1 bit per pixel, which was either 0 or 1, which allowed us to only have 2 colours. The second example showed us using 2 bits per pixel, which gave us 4 colours. Now, using 4 bits has allowed us to have a lot more colours. We then moved on to SketchUp, which was 3D graphics, and again, have a look at the toolbar, make sure that you can name and describe the different tools and why you would use them in different circumstances. Think of the ones like pan, rotate. Do you know the difference between those? Offset is this one here. Okay, so if you've got a shape and you want to duplicate that shape but make it either larger or smaller, you would use offset. Extrude is your push-pull tool, which is this one here, and then we have our orbit. Okay, so that's not rotating the shape, that is moving our camera angle around the shape. And what is meant by 3D? Well, remember it's 3 dimensions, and those 3 dimensions are X and Y in order to give us a kind of 2D shape, and then we introduce the Z in order to give the third dimension, which is depth, which gives it that 3D feel. We then moved on to the idea of capturing graphics. How else do we obtain a graphic and have it digitally on our computer? This then led on to the idea of resolution and how different devices can have resolution as a measurement of how good quality is. Now in this example we've got a digital camera which is measured in megapixels, and you can see here this one has a resolution of 20.3 megapixels, which means 20.3 million pixels in every single image. Resolution isn't always in megapixels and can be measured in DPI, which is dots per inch. In this example, the scanner has a resolution of 4800 by 9600 DPI, which means it has that amount of dots per inch. Again, this is a good indication of the quality of the scanner. The higher the resolution, the more detail this scanner will be able to achieve. Printer resolution is also measured in DPI, so if you were going to be buying a new printer, the resolution would be one of the main considerations for you. This one has a resolution of 2400 by 1200 DPI. Another consideration is just the specification which is underneath, which is up to 8 ppm, which is pages per minute. When it comes to a monitor, the resolution is measured in the number of pixels horizontally by the number of pixels vertically. In this example, we have 1920 pixels going across the screen horizontally by 1080 pixels going up and down the way, so vertically. In class, we watched a video of somebody using a graphics tablet. Why would you want to draw digitally rather than drawing on a piece of paper? Well, we got to think about the accuracy, the ease of duplication and fast production of shapes, large range of tools and effects that you might not be able to do with the materials that you have physically, and special effects that are not available by hand drawing. Why would you perhaps want to draw by hand rather than using a computer and say a graphics tablet? Well, a mouse can be clumsy and inaccurate. Textures and effects that you can touch as well as be seen. There might be a bit more texture that you would have by using a particular material. No technical issues, so power failure, printing, hardware failure, no computing skills required, and also it's probably going to be a lot cheaper than buying all the technical equipment that you would need to use a computer for digital drawing. We then moved on to binary numbers. These numbers should be familiar to you, and these are the columns that we use in order to create a binary number. Remember the 3 rules of remembering these numbers. We start off at the right hand side. We start off with the number 1 and then we move back to the left, doubling it every time. So we start off with 1, 2, 4, 8, 16, 32, 64 and 128. So if we wanted to make a number such as 36, well, at this point we start off at the left hand side and say, do I need 128 in my number in order to make 36? No, I don't. Do I need 64? No, I don't. Do I need 32? Yes, I do. Okay, so the first 2 numbers were too high. 32 works in my number. If I added 16, it would be too large. If I added 8, it would be too large. If I added 4, it would give me 32 plus 4, which is 36, which is the number I want. So I don't need to check 2 and 1. For the remaining numbers that I have not used, I put a 0 underneath each one of these, which then gives me the proper representation of 36 in binary 0, 0, 1, 0, 0, 1, 0, 0. Again, pause this part of the video in order to test yourself. Try and create the numbers on the right hand side by using binary, by using the same technique, starting from the left hand side. Take the first number which will work inside yours, so 16 plus 2 plus 1 will give me 19. Also, you can try by taking these numbers and covering the red numbers in order to work out what the binary represents. Then we moved on to binary text and this word ASCII. And so you should know that this stands for American Standard Code for Information Interchange. Remember, it was developed in America. It uses our alphabet. It's a standard, which means that all computing devices use this same code. The code is for information interchange, which means that the information or the data can be exchanged between 2 or more computers. The things you should remember about ASCII are that it uses 8 bits. So for example, a character could be represented by 0110 1001. That means it can store 256 characters, which includes all of our uppercase, our lowercase letters, numbers, control characters, which are things like escape, shift and control. Then we moved on to our web design unit, so our HTML and our CSS, our styles. Okay, so HTML first of all stands for Hypertext Markup Language. And this is what the kind of standard structure of a web page would look like, a very simple web page. We start off with our HTML tag, and you can see we also end with that. Remember, every time you open up a tag, you have to close it using the / before the tag name. The second tag that we would use is the head, and again we close the head. Inside the head we can have the title of our web page. Now the title is not heading, this is not shown in the content of the page, this is actually shown at the top bar of our browser. Then we have the body. Now this is a content, this is anything which is shown in our web page, and in here we have H1, which is the largest heading we would have. Remember, H2 would be slightly smaller, H3 would be slightly smaller still, and so on. P means a new paragraph, so every time you want to start a new paragraph, you start a new P tag. Some people mistake H1 as the first heading and then H2 as the second heading. Remember, this refers to the size rather than the number of headings. This is the code for images, so IMG, SRC, we are taking away our vowels and we end up with this code. So again, it's just a case of remembering this. Do go to W3 Schools and try some of the examples again, as well as the information which is on Schoology. Styles allow us to change the appearance of our web pages. And by adding this code into our head part of our HTML, it would allow us to change all H1 tags to have the font family Arial, all paragraphs to have a font family of Comic Sans, and again for all H1s to have a font size of 24 pixels. Here's another example that you can work through, and we haven't mentioned it yet, but note the hex code or the RGB code. You will need to revise this as well, and again, that means that our body background would have this particular colour. You can maybe try and work out what that colour would be. H1 would have a text colour of white. H1 would also have a font family of Arial. Paragraphs would have Comic Sans again, and then H1 would have a text align of centre, which means all headings will be centrally aligned. This is one of the larger bits of code, creating a hyperlink. A is for a hyperlink reference, so ahref equals whatever hyperlink you want to use, close the tag, and then we have a bit of code which you want to look like a hyperlink, so that would be blue and underlined, and then we finish off with the A just singly on its own. You don't need the href at this point, it is just A on its own with the close tag sign. Okay, so when it comes to colours, such as text colour or background colour, we can use the name of a particular name of colour. But sometimes they don't exist for the exact colour that we are looking for. So we use a hex code. Now, if we have a look at the top example, which is our slate grey, we've got 708090. Now, if we split these up into twos, okay, the first two numbers represent the amount of red, the next two are the amount of green, and the next two are the amount of blue. Okay, so you can see here we've got slightly more blue, we've got a kind of medium amount of green, and we've got a little bit less red. If we wanted it to be more of a blue colour, we would increase this number. Now, when we have our numbers, we go from 0 to 9. Okay, but that's not enough to represent this, so we then need to go to A, B, C, D, E, and F. So you can see here FF. Okay, so there's the most red that can have. You can see this is a red colour. When we are down here, we can see we've got a lot of red, a lot of blue, so we've ended up with a kind of purpley pink colour. So you should be able to work out why using a particular code would give you a particular colour. Yellow is quite an interesting one. We are using light in order to make up our colours rather than paint, and if you add red light and green light with no blue light, it gives you a yellow colour. We briefly had a look at Sony Acid as well, where we created some excellent songs. Again, just be aware of the sort of tools that we used and the different effects. Think about the words pan, and how we would maybe pan this. Did we use any fade-ins, etc. And last but not least, we may have a couple of questions in the end of year assessment about computational thinking. That was the idea of Bebras or Scratch or Microbit, using sort of algorithmic thinking, so algorithms, programming code, in order to come up with a solution. Can you look at something like this on the right hand side in order to determine up, right, down, left, where this ball is going to end up? Again, you can have a look at these different websites, so Compute, IT, have a look at the things we've done on Schoology in the past in order to give yourself a little bit of practice for this type of thing. Okay, so good luck, get studying, and get in touch with either myself or Mr. Harkins if you have any questions for the upcoming end of year computing assessment. Remember, this is not all you should be doing listening to this presentation. Have a look at all the resources which are available on Schoology and get active in your revision, making up your own flashcards, mind maps, and anything else that you think would help. Okay, good luck.